Well, polar coordinates were introduced towards the end of 119, and we did not see any benefits of polar coordinates considered by then. But now we will be using them in double integrals, and this system, this polar coordinate system, will be extremely useful. Let us recall what polar coordinates were in plane. Namely, it was the following. For a point xy, we connected that to the origin, and this length was denoted by r, and the angle with the positive x-axis was shown by theta, and of course by the right triangles that we form here, we immediately see the conversion formula. Namely, one had that r was, x was r cosine theta, y was r sine theta, and of course by the Pythagorean theorem, the sum of the squares was r squared. So, of course, you can also choose theta from here, namely, theta would be y over x, and then you apply arctangent, etc. That's not a very particularly useful formula, so we will not go into that, but of course it will come now and then. And there were some features. Namely, we could, of course, express certain curves in polar coordinate system, and this was so especially in some cases when Cartesian coordinate system would be extremely cumbersome, very complicated, and polars gave us very nice formulations. Namely, r could be expressed as a function of theta, and we could sketch these curves. The basic idea behind these sketches was point-by-point sketching. Namely, we just found some points, connected them, and that was the curve. Okay. And some examples were the following. Okay, these will be of use as well, so a review could be very useful. For example, say r is a cosine theta. Okay. Now, when we look at this formulation, we don't see much actually, but we could multiply by r. Then this becomes x squared plus y squared, and this becomes ax. Okay. So this formula simply means that we have x minus a over 2 squared plus y squared, and that is r squared. That means a squared over 4 here. Let me check if I'm correct. You have x minus a over 2 squared, so you have a over 2 squares. So this is actually a circle. Okay. It's a circle with center at a over 2, 0. And the radius is a over 2. Okay. And this is a. A point-by-point sketch clearly gives this. I will not go into those sketches. Well, for example, r is, say, 2a sine theta. By the same token, namely, multiplying by r is not harmful in the sense that r is positive. Okay? So whenever you multiply both sides by r, you don't lose anything. If r is 0, which is possible, you can compensate by changing theta. Namely, some thetas, that is cosine theta, will be 0 at pi over 2. So r being 0 is irrelevant here. Well, so let us apply the same trick. This, of course, now says we have x squared plus y squared, that's r squared, is r sine theta, which is y. In other words, this is now y minus n squared, is a squared. Okay. So this time it's a circle with radius a, center at a0, so it's like this. Okay. So the equation in polars is given by this formula. Well, all the famous examples, one has the cardioid. Okay, say r is something like cosine theta plus 1. Okay. Now, a point-by-point sketch, I will not do it in detail, but roughly speaking, when theta is 0, okay, you end up at 2 in this example. And when theta increases, cosine decreases, so you end up with something like this. These are ones. Now, in these sketches, it's important to note a few things. Firstly, okay, r normally starts from 0 and can go up to infinity. It's positive, it's a distance. Theta can start from 0 and go to 2 pi. Then, of course, you cover everything in the plane. But when you discuss, for example, something, a formula like this, it may happen that sine theta is negative. That means r is negative. Now, this is problematic. Okay? Actually, it's not. With the following interpretation, which we introduced last time when we discussed polars. Now, in some equations, r is f of theta, okay, or functions, whatever, okay. Sometimes negative r can occur. Okay. Now we interpret this as follows. Okay. Well, a negative r means adding pi to theta. In other words, taking symmetric with respect to the origin of the point absolute r and theta. This means the following, of course. For example, okay, say -2 and pi over 4, here this is r, this is theta. This means the following. Firstly, okay, we draw the point which has, okay, absolute minus 2, it's a positive number, that's r, and pi over 4 as usual. Okay, now this is not our point, and then we take symmetric with respect to the origin, we get Rp. Okay. So this is now P, which is minus 2 and pi over 4 with R and theta, whereas this point would be 2 and pi over 4. Okay. So whenever we have a negative R, this reflects in our sketch as taking the symmetric of the point with respect to the origin. Now, with this understanding, everything fits to be okay. Now, to apply polar coordinates or to use polar coordinates in double integrals, okay, we will observe a few things. Now let us recall that roughly a double integral over D is the limit of the double sums of f of pij's times area of rij's. Here I'm not going to details, namely we assume f is 0 outside a rectangle containing D. We discussed them at the very beginning of our introduction to double integrals. Now, geometrically, what does this mean? This means the following. We have some D here. Okay. We divide it into little rectangles. Okay. You can call this the Rij rectangle. And at the top, we have, well, you can assume f is positive for simplicity. So we have some surface. It doesn't matter if f is negative. And then, okay, we multiply this area with a height, hij, which could be the maximum of the function f, or the minimum. We take upper or we get upper or lower Riemann sums, or an arbitrary point in D, as in this Riemann sum formulation. Okay. So to find the volume, for instance, okay, if we do this and these rectangles are small enough, we get a pretty good approximation. In the limit, okay, we get the area, the volume in question in the sum. So far, these are our discussions. Now, a good question is, why did we choose rectangles? Okay. One reason is obvious, because in one dimension, we divided the interval, okay, AB, into small pieces. And we also did the same thing for the y's. When you put them together, you get rectangles, of course. Well, the question is, what would happen if we did not use rectangles, but triangles? small triangles. Okay? Suppose we took D other small Rij, which are not rectangles. Okay. For example, something like this. Okay. We have our D here again. Say we divide that into small triangles of this form. And so at the top, okay, we would have a triangular shape on the surface, and we would still choose a point in this triangle, multiply it, okay, with the area of the triangle. So call this Rij. Now maybe let me say Pij, for example, a triangle. And we add them together. Okay. Wouldn't we get the same volume in the limit? Well, of course. Why not? Of course, here, the triangles must get smaller and smaller in the limit. They must shrink to a point in the limit, which is what we did with rectangles. So rectangles are not very special at all. Actually, they are in some sense, but there is no problem if we replace small rectangles with triangles or other little pieces of regions. Okay. Well, in the limit, we would get the same number. Namely, the double integral, which is the limit of the sum of Fpij stars times area of rectangles, is the same as the limit of f of Pij stars. Of course, Pij star is in Rij, but area of Tij's, the triangles. Okay. Triangles are not used in general because rectangles are easier. But apart from that, theoretically, we should get the same thing. Now, there is an important reason why we use rectangles, which is not related to simplicity of calculation. It is that rectangles, small rectangles, are bounded by sides which are parallel to the axes. In other words, on the sides of a rectangle, either x or y is constant. So, note that on the sides of Rij's, rather, just the sides of Rij's are parallel to x or y axis. In other words, x or y is constant. So the rectangles are so formed that their sides are nothing but x or y is constant. Now, let us consider a partition like the following. Okay, suppose we have a D, a region in xy plane, and we partition it with theta or r is constant. Okay. Namely, what does that mean? Theta constant, remember, was a half ray. So let me use this. Okay. Now, theta constant means something like this. So let us divide it into pieces like this. You can enumerate them if you want. For example, the first one, say, is theta 1, or rather say, okay, A. The other one is, this is theta 0. The other one is theta 1. And you go up to this biggest theta, which happens to be theta n, which is B. Now, this looks like a nice enough partition. Okay. So, you gradually increase your angle, and then, okay, you trace all of D. In the meantime, well, why did we want theta constant? Because we want this situation look like the Cartesian case, where x or y is constant. Here now, okay, thetas are constant. Okay. We have, okay, let me just put here some standard case. And now, let us also sketch the curves where r is constant. Well, r is constant means we have circles. So they would look like the following. Okay. These are r is constant curves, and these are theta is constant curves. And at the end, okay, let us take a piece from here. Now we can call this piece something like, okay, Sij, because, okay, one index comes from thetas, the other comes from r's. Of course, r's, we can draw more circles like this, but we are outside of D, and therefore it's meaningless to sketch them. So, okay, let me make this a little bit bolder so that we can see what's happening. Okay, this is our D. And we have one piece which could be, okay, called Sij. So now we have the following. Okay. Firstly, okay, let us form the sum. So limit of the double sum of fpij star, where this is an element of Sij, times area of Sij is actually the double integral of f direct. That's what we discussed a minute ago. Well, the question is, what is the area of Sij? Okay. We can easily check that. Namely, okay, we have two thetas here. Say this is delta theta. And we have two circles. Say this length is delta r. We want to calculate area of Sij. Okay. Well, we have, of course, one simple thing here. That's to say, recall that by direct proportionality, okay, in a circle, if you have some alpha angle, okay, and the radius is r, then area of the wedge, okay, corresponds to the angle alpha, and of course pi r squared, the total area, corresponds to the total angle, which is 2 pi. So one has area becomes pi r squared alpha divided by 2 pi, or just r squared alpha over 2. Okay. So, okay, area of Sij is a difference of two areas. Okay. One is, you can, okay, call this smaller one r, the bigger one r plus delta r, for instance. Then it would be, okay, r plus delta r squared, alpha is delta theta, minus r squared delta theta over 2. Which means, okay, you have r squares canceling out, so you have 2r delta r coming from here, delta theta over 2, okay, plus the last term, delta r squared delta theta over 2. Which means, if we take delta r and delta theta and r out, okay, we have 1 coming from here, and delta r, actually, let me not take this out. Okay, let me leave it here. It's r plus, these cancel out. Delta r, delta theta is taken out, so it is delta r over 2. Now, if delta r is very small, this looks like r delta r delta theta. Okay. So, these areas, of course, here, where do the indices ij come into the picture? Well, delta r is actually ri minus ri minus 1. Delta theta is theta j minus theta j minus 1. So this product is dependent on I and j if we want to be strict and make the analogy to Riemann sums. So we get then this is the limit of a double sum where we have fpij stars. Here these belong to Sij's times the area of Sij. Well, the area of Sij was nothing but, okay, r times delta r delta theta. Now, note that this is the area of, okay, a rectangle. Okay. One is a difference of r's, the other side is a difference of thetas, but not in the xy system. In the r theta plane. Considering this part as your function value, then this is the limit of something like delta x, delta y. R and theta are not important here. Just think of the usual Riemann sum. There we had a function, and we multiplied by the area of Rij, which was nothing but delta x times delta y. So here, this is then a double integral of f, but we have delta r, delta theta. So it is in r theta system now, because this is a rectangle in the r theta plane. And how do r and theta change in the r theta plane? They don't change in the original D anymore. They change in a new domain. But except for the change of names r and theta, okay, here of course we have an r. Except for the change in r and theta, this is the standard double integral we have. Actually, the conclusion is that if instead of looking at rectangles, you look at some other small partition where the smaller Sij's are not rectangles anymore, then actually you are doing a change of variables in a double integral, as we have here. Okay. Now, in such cases, we will go into details there later for the general change of variable. But for the time being, to understand what's happening, okay, let us consider an example. Okay, let d, which is actually dxy, be the following. Okay. Suppose it is something like this. It's a wedge. This is, of course, a circle of radius 2. So this is our d now. Now we want to write our double integral in terms of polars. That is, using this. So our double integral fxy dAxy, I will put an xy here, meaning these are the x and y's. Okay. I want to write this in the r theta system. Now, how do you transform a region to a new coordinate system? Well, the region is bounded by and determined by, okay, its boundaries. So, transform the boundaries. And what are the boundaries here? Well, we have x squared plus y squared is 4. Now this changed into r is 2, because the radius is 2. And okay, we have y is x, that is this line, but that transforms into theta is pi over 4 directly. And of course, we have the x-axis. It transforms into theta 0. So, putting them in place, we have then, okay, r is 2, r is 0, and theta is, sorry, I didn't say this yet, but it will come in a minute. Okay, theta is 0, so we have this. And theta is pi over 4. So we see that actually here we had 3 boundaries, and we have 3 boundaries here, but one side is open. Well, it's not logical. Okay, actually there are 4 sides. Namely, here we have 3 curves bounding this, but there is a 4th curve when you pass to polars. That is the curve r is 0. R changed from 0 to 2 here. So r starts from 0, and therefore, okay, actually r is 0 is a boundary. Okay. So putting this in place, we have, so this is our dr theta. Now, well, life looks well because we had a very strange looking, okay, piece here, but now we have a nice rectangle. What else do we know? Well, we know the following. We can now calculate using the polars at this point. So, say we want to calculate the area of the xy. So, area would be integral of 1 dx. Okay. A word of warning, area is defined as the double integral of 1 only for Cartesian coordinates. Okay. By putting 1 in a new system, you don't get the area. You get a different thing, actually, because areas are not preserved when you change variables. We will discuss these later. So let us start from the original. These are all in the xy coordinate system. Now, we already know that if we change this to polars, we will get a new dr theta. We will have an extra r coming, and we will have dA r theta. Well, what is dr theta? It's a rectangle. And this is very easy to evaluate then. It is r, for example, dr theta. R changes from 0 to 2. Theta changes from 0 to pi over 4. Okay. The important thing is we have an extra r coming. Okay. This is coming from the change of variable. We will understand it later in a much detailed way. Well, what is this after all? It's r squared over 2, so it's 1/2 times 4 times pi over 4, which is actually, let me see, did I do it correctly? Yes, it's pi over 2. Okay. Well, does this make sense? Well, of course it does, because after all, the area we calculated is 1/8 of the area of a circle. Okay, so geometrically, okay, area is 1/8 of area of circle with r equal to 2, which is, of course, 1/8 times pi r squared, so it is pi over 2. So we expect this, because this is a simple example. We are calculating area of a 1/8 of a circle. But you see how simplified the calculation is here. Okay. If you wanted to calculate this directly by using x and y's, okay, the region would be normal or simple with respect to x first, so you should change x equal to whatever you have. You would, of course, get square roots, and you would need to do inverse trigonometric substitutions. So this simplifies the calculation a lot. Now, the next question is, of course, when can we change a double integral in polars into iterated integrals? Well, the answer is the same. Okay? Whether you use x's or y's in xy plane, or r's and thetas in r theta plane, the basic principle does not change. Simple regions are the same simple regions, but there is a practical difference which we will exploit in a minute. Well, clearly, in the r theta plane, okay, a simple region means, for example, if we are looking in the r direction, it will be a first curve, okay, r is some g of theta, and the second curve, r is h of theta, and the sides will be vertical from, say, theta 1 to theta 2, and this is, well, by our definitions, a simple region with respect to r first. And, of course, again in the r theta plane, okay, if you look in the theta direction first, you have a curve. Theta is g of r. And next, you have a different curve. Theta is h of r. And you have horizontal lines, say from r1 to r2. And this region is simple with respect to theta first. So this is exactly the same type of definition that we had before. And therefore, in this new set of variables, we can use our iteration theorems and so on. Okay, let me say and, okay, iteration theorem is valid since we only changed symbols from, okay, xy to r theta. Why do I say that? Well, forgetting the meaning of r or theta in Cartesian. In the r theta system, call this x, call this y, then you have y is h of x. It's exactly the same thing as we had before. But what does this mean in Cartesian coordinates? Now, this is a different story. Okay. So once we get these, we can directly pass to iterated integrals. That's not a problem. But how do we recognize such a region without passing to our theta system? Now, this means, okay, in xy coordinate system, the following. Let us see. We are looking in the r direction. But what is the r direction in xy system? How does r increase? Okay. R increases starting from 0 in all directions. So, okay, we look at the following. This is increasing r direction. Because when you go away from the origin, r increases. Fine. Okay. And then you start increasing r, you hit a curve. Now this curve must be translated into xy system. Assume it is. It's still a curve. Okay. So we have a curve here. Okay, let me write it in its polar name. R is g of theta. But it must be transferred into x and y's. And you start from here and increase towards another curve. Say this is now a curve which is h of theta. Okay. So you started from here, you hit this, and you move on. Okay. You are now between these curves, so these parts don't count. These are the important ones. Okay. Your r enters the domain at r equal to g of theta, and then it increases up to here. In the meantime, theta changed between two constants. Well, theta constant means, of course, that you have here something like this, and here perhaps something like this. So, what is a simple region then in polars, but observed in XY system? It's something like this. So this is, such a region is simple in polars, but it's sketched in Cartesian. So in the Cartesian system, when we see a D like this, we recognize that it's simple with respect to R in the polar system. Okay. Let us see what the other one looks like. Similarly, in the Cartesian system, now we are looking in increasing theta direction. Now, how does theta increase? That is the angle starting from x. Okay, here the angle is 0, and when you move counterclockwise, it increases. So this is the increasing theta direction. Now, as theta increases this way, it hits a curve, okay? The first curve, theta is g of r, perhaps something like this. Okay. Sorry, it's nonsense. Okay, it hits the curve here. Okay, it starts from the curve. These are not inside yet, and you move on until you hit another curve, which is theta is h of r. This would be theta is g of r. Okay. So you move from one curve to the other, okay, in the increasing theta direction. Okay. In the meantime, R changed between two constants. So, what were our constant curves? These were circles. So you have somewhere here a circle, say with radius r1, and somewhere here you have a circle with radius r2. So a standard simple region with respect to theta first looks like this. Firstly, it must lie between two circles. And in the theta direction, you must have curves. So this D2 is simple with respect to theta first. Okay. Well, this is what happens in the XY system. Okay, but originally our domains are given in XY system, usually. And we can directly recognize if it's simple with respect to theta or r or neither. Okay. And once we have such a structure, we know it is simple with respect to the appropriate variable first. Well, examples will clarify this, of course. So let us consider some examples in it. Okay, the question is express in polar in iterated polars. So, first of all, D is the upper circle. Okay. The half disk, that is. And this is x squared, y squared is r squared. So, we want to express I, which is an integral over D. This is, of course, dxy. We are not in polars yet. Okay, we have some f, and we have dA all xy's. Okay. Now we want to show this in polars, in iterated polars. Well, that means, of course, that we change I into polars first. In polars, that is dr theta, remember, f. Okay, now we are making a change of variable. So there will be no x's or y's left. Everything must be in terms of r's and thetas. So instead of x, we write r cosine theta. Instead of y, we write r sine theta, apply our function. And now we have some r here, factor coming, because we use polars. And the rest is, everything now is in polars. Okay, we are finished as a double integral. Now, we want to write this in iterated polars. That means we look at this region and see it is simple with respect to r or theta. But which one? Actually, it's both. Okay. Now, this region is simple with respect to r first because, okay, let us look at this more carefully. Again, everything is yet in the xy system. Okay, this is the region. Now we start from the origin, look in our increasing direction. Okay, these are also possible, but they're outside D. We don't care. Now we move up to the circle. The first curve is this. The last curve is this. So this is the first curve. Because when r starts from the origin, it's immediately inside T. So that must be the first curve. Well, it doesn't look like a curve. Okay? Actually, it is a curve. R is 0, or namely a circle with radius 0. And the last curve, where it leaves, okay, the domain is, of course, R is capital R. So R changes between two curves. In the meantime, theta must change between two constants. Well, clearly, the first value of theta is 0. It moves up to pi. Okay. So, B is simple with respect to R first. So, the integral becomes f of r cosine theta, r sine theta, r dr d theta, and r changes from 0 to capital R, theta 0 to pi. we observe here at the same time that this half circle is actually, from these, a rectangle in the r theta system. So it chains circles to rectangles. And life is very easy after that. Okay. Because it's a rectangle, in rectangles you can look in either direction. So it's the same as the following. d theta dr, and theta change 0 to pi, r 0 to r. This is because since dr theta is a rectangle. In rectangles, you can just change the places because whichever way you like, nothing changes. Okay, you don't have other variables in it, just constants everywhere. So this is indeed a region, that is this one, in xy system, which is simple both with respect to r or theta first. And we wrote iterated integrals accordingly. Okay. Now, okay, as a second example, okay, let D be the following. It is a wedge, like this, where this line is y is x, and this line is y is cube root of times x. Okay, and we have a circle bounding it. So this is our D, but this happens in the xy system. Okay. Well, does this look like, okay, a simple region? Yes, of course. Okay. Actually, it's a rectangle. Okay. So D is simple. With respect to both, okay, r and theta. Let us just express it once, namely, okay, let us take, say we write r first. Then the integral over df dA, all in the xy system, would be in the r theta system, f r cosine theta, r sine theta, r times, okay, dA r theta. Now in iterated form, why did we say this wedge is a simple region with respect to r first? Well, because r starts from 0 and goes up to 2. Okay. In the meantime, theta changes between two constants because a half ray means theta constant. What are these constants, by the way? Okay. We need to find the value of theta. Okay. So, since we have here, okay, y is x, okay, then, of course, clearly, theta is pi over 4 because, I mean, tangent is 1. Similarly here, okay, y is cube root, square root 3 times x. Well, this angle, then, that is, call this theta 2, okay, tangent theta 2 is, of course, root 3. Okay. So, theta 2 is pi over. Well, thus, I becomes f of r cosine theta, r sine theta, r dr d theta. R changes from the picture directly, 0 to 2 but these are curves. Okay. And theta changed from pi over 4 up to pi over 3. Okay. The rest is usual calculation, would be usual calculation if we knew what f was. Okay. Now, because this is a rectangle in polars, of course, we can change the order just like that. We don't have to worry about it. Okay. A third example. This time, let D be, again, a wedge-like thing in the xy system. Okay. These are the lines, y is x, and y is minus x, and y is 1. Okay, everything in xy system at this point. Well, let us try to observe if this region is simple with respect to R first. Well, R starts from the origin. We are already inside. We move, and we leave from the same curve. So, okay, and in the meantime, of course, theta changes between two constants. Okay, this curve is, theta is pi over 4, and this curve is, theta is 3 pi over 4. So theta changes between constants, so this is simple. So we can directly write an integral over b f dA, well, all xy. I will not write these indices anymore. I'm just writing them at this point so that we are not confused, because we have r's and thetas as well. This would be integral of f, and I'm not writing r cosine theta, r sine theta anymore, but they are there, times r dr dθ. Now, r starts from the origin curve, that is 0, goes up to y equal to 1. Now, what is y equal to 1? It must be expressed in polars. So, here, okay, y equal to 1 means, remember, this is r sine theta. So, r is, okay, 1 over sine theta, or cosecant of theta. It's 1 over sine theta. So, we have here cosecant of theta. And, of course, theta between two constants, pi over 4 up to 3 over 4. So this would be that expression.